Hey everyone, so today we're just going to start with, on Chapter 1 in the Stat 200 workbook. And we're going to start Part 1 on significance tests, Type 1 and 2 errors, and power. So let's all turn to page 1 and begin. So you all remember that a significance test, otherwise known as a hypothesis test, these mean the same thing, is a statistical test to determine whether some difference we observe is real, meaning due to some particular cause, or just due to chance variation, the luck of the draw. And we set up what we call a null hypothesis, abbreviated by H naught. The null hypothesis. I like to think of it as the dull hypothesis because it's usually the hypothesis of no effect. The population parameter is a particular value, and any observed sample differences from that value can just be explained by chance variation, the luck of the draw. So the null hypothesis is generally the hypothesis of no effect. Whatever effect we see in our sample is just due to chance variation. So if we're testing a treatment, the null is that the treatment didn't work. All right? Now, you also have an alternative hypothesis, abbreviated by H sub A for alternative. And this hypothesis says no, the difference you see in your sample compared to what you'd expect in the population is due to some other reason besides chance. There's some other reason that explains the sample data. It's the hypothesis that the effect we see is real. So if we're testing a treatment, the alternative is that the treatment worked. Now, let's look at this in the context of a randomized double-blind experiment because it translates very nicely into a significance test. And also, it's really helpful to just always think of an example. And I hope this example will stick in your mind. And let's say that we wanted to test whether some drug that there were already preliminary results in the lab that it proved that it seemed to help people learn statistics better. And now, and it was proven to be safe, and we said, okay, let's test it in our Stat 200 class. So we have 300 people in the class, and let's say I randomly divided you at the very start of the semester into two groups. And half of you were randomly assigned to take the real drug. Let's say it was a one-time pill. That's all you had to do. Half took it. And the other half took a placebo, a sugar pill. And you didn't know which group you were in. And I didn't know which group you were in either. And that's called a double-blind randomized experiment. So let's fast forward to the end of the semester, and it's time to assign your grades. So I know everybody's overall percentage of how they did in the class, and I break the blind. And I say who was in the drug group and who was in the placebo group. So I say, how can I see if this drug worked? Well, one way to evaluate the effectiveness of the drug, probably the simplest way, would just be to compare the means, the averages of the 150 people who took the real drug, and compare it to the average of the 150 people who took the placebo. Compare their overall percentages, right? And let's say we did that, and the mean, the average for the treatment group was higher. It was higher, all right? So the question is, how much higher does it have to be before you can conclude that the drug worked? Would any bit higher make you believe the drug worked? I mean, if it was just a tiny 0.5% higher, or I mean, if it was dramatic, like if the people who took the drug got 95%, the people who took the placebo got 60%, we wouldn't need a significance test to tell us whether the drug worked. But so how are we going to figure this out? The idea is that you assume that the drug didn't work, right? You assume the drug didn't work at all, and you wonder under, let's say it didn't work, what's the probability that we'd see such a difference just due to chance variation? So let's go through this idea, and it's an argument by contradiction. So you assume the null to be true, that the drug worked no better than the placebo, okay? And you set up what's called a probability model. We're going to set up a box model, which is a box filled with tickets that have numbers on it. And then we're going to randomly draw from that box. It's a very simple probability model. Assuming the null to be true, based on the null. So we're going to try to translate. It's very easy to translate that situation of randomly assigning people to two groups into random draws, into a probability model. And all statistics, all inferential statistics, is based on probability models. All right? And so then we ask if the results you found were very surprising if the sample was randomly drawn from that box. Okay, so let's picture the box. What would be the simplest box? Okay, I think the simplest box would be, just imagine putting all 300 overall percentages, all those, we'll write those on tickets, stick them in the box. So we have 300 numbers in the box. We shake them up, we shake up the box, and then we randomly divide those tickets into two groups, right? And we take the average of the two groups, and we see how likely it is to get a difference as big as the difference we got. Well, we do this over and over and over and over again. We look at the difference. I mean, so let's draw this picture and think about what it might look like. Let's set this up here. Okay, so you have, let's write this down. So we have this null hypothesis that the difference in means is 0. And that's the same as saying the drug didn't work. It's the same as the placebo. All right, and then we have the alternative hypothesis, which is usually what we're trying to prove. Certainly here, we want to know if the drug, we're hoping the drug works. And then the difference is not equal to 0, the difference between the two means. And we even know that that in this case, we expect that the people who took the real drug would do better. So the difference is greater than 0. The treatment mean minus the placebo mean is greater than 0. Okay, and that means the drug worked. The difference we see is too big to be explained by chance. It must be real. It must be due to the drug. Okay, so now imagine that you have these 300 tickets in the box, you shake them up, you randomly divide them into two groups, you take the mean of each group, subtract them, and do this over and over and over and over again. We know by the central limit theorem that this is the sampling distribution of, let's read right here, of this test statistic will follow the normal curve. And if we translate it into a z-score, let's look here. So you pick a statistic for which you'd expect the null and alternative hypothesis to give different values. And for example, a sample mean. That was intuitive in this case. To see it, you could pick other statistics, but the mean makes sense in this case. To see if it's outside the range that you'd find just by random sampling from the null box, you make a version of that statistic with a known sampling distribution for draws from the null. For example, the sample mean divided by its standard error estimated from the sample. So that's what we're going to do here. We're going to pick this our test stat that's going to measure, evaluate the evidence for whether the drug worked, is going to be a z-score, which would be what? The difference that we see in our sample, we'll call it our observed difference, minus what we'd expect under the null, the expected difference, divided for the typical difference. the typical difference we'd see, which is the standard error for the difference. And that's going to depend on the variation of the scores, and it's also going to depend on how big a sample size we have. And if the sample size is big enough, like it is in our case, it's going to follow very closely a normal curve like this. Okay? So what we're talking about here is this is the difference in means between the treatment group and the control group. So another way of writing this would be X bar for the treatment, that's an abbreviation for the mean, for the sample mean for the treatment, minus the sample mean for the placebo group, minus 0, this is just 0, over the standard error. And we'll look at the formula for the standard error later, the standard error for the difference of the two means. Okay, so this is what's known as the sampling distribution. It's a probability histogram representing the chances. The whole thing adds up to 100%, and it represents the chances of getting every possible difference. We'd expect to get 0 difference, and once we translate it into a z-score, about 68% of the time, we'd expect to get between a z-score between 1 and -1, and 95% of the time between 2 and -2, and it's going to be very rare to get outside the limits of -3 and 3. That's like 99.73% of the time. So now we want to know we're going to look at what z-score. So we'd expect to get 0 difference, a z-score of about 68% of the time we're going to get a z-score between 1 and -1. So we look at our z-score and we see where it is on here. Now let's think about what this means. We expect, if the null is true, we're going to get something way out. We're going to get a big, big difference between in terms not likely to be due to chance, right? What about if we just got a little difference like this? Or over here, that looks very, look at between 1 and -1, 2/3 of the time we're going to get here when the null is true. This is a sampling distribution when H0 is true, when nothing is going on. We don't expect to get exactly 0, right? Around that is likely, but look at, in fact, we could get, imagine this, what if just by the luck of the draw, isn't it possible that 150 of the highest scores, the top 150 scores, landed in one group and the bottom landed in the other? I mean, that's as likely, really, as any other single ordered possibility. There's just a lot more ways to get close to here than to get that particular. That would be way out here. Can you imagine that? I mean, it's possible, right? And that would be overwhelming evidence. And it would be so unlikely, but it's still possible. All these probabilities is what I'm saying. This whole curve represents when nothing's going on, when the drug didn't work. All right? So now we see, let's say we did all this, and we get some difference, and we translate it into a z-score. And let's say we see some difference, right? At what point would you say, hey, that's just too far out of the range? How far do I have to get before you'd say, hey, I'm going to say the drug worked? That's not just chance variation. All right, so why don't you just tell me, by the way, what if it goes this way? What does that mean? That means if it went extreme far out here, that would mean that the drug makes you dumber, makes you learn statistics. Very, like all the people who took the drug did way worse. And we already have evidence. We expect it to go this way, and that's why we have what we call a one-sided hypothesis test, and we have a directional alternative. If I just thought it's going to be different, then there's going to be some difference, but I knew the drug was going to do something. I mean, this happens sometimes. You know it's going to do something, but you don't know if it's going to be better or worse, and then I'd have a two-sided hypothesis test and an inequality here instead of a greater than, just not equal. All right, so you stop me, okay? Tell me where, just intuitively, you get a result. At what point, when I trans along here, would you draw the line and say, hey, I'm going to draw the cutoff there and say the drug worked? How far off does it have to be? Okay? You got to tell me when to stop, okay? So here I go. Okay, right there. Okay. Stop right there. I'm going to keep going. Some of you may disagree. Tell me where you think I should draw the line. Tell me where you think I should draw it. Somebody said here? Okay. Here. You want me to go further? Let's just say it was, you said here? I'm going to start again. Okay. Don't pay attention to these numbers. You think it has to start at a, okay, we're on the curve. Just tell me. Okay, right there you say? Okay, so we have this one, and this one to compare. All right, so let's compute what's called p-values for these. So if you want to draw the line right here, you're saying at this point, if you get a higher z-score than that, you're going to conclude that the drug worked. You're going to reject this and conclude the drug worked. And this, it looks to me at about like it's about 1.65. So we want to find out what this area is from here on in. That's called, let's go to back to our notes here, and look at what we're doing here. So we pick a statistic for which you'd expect the null and alternative to give different views. We already did that. And to see if it's outside the range that you'd find just by random sampling. All right, we did all this. Check how likely it would have been to get our data's test stat, or one even farther, from the null if the null were true, and that's called the p-value. All right, so what we're doing now, what you guys intuitively said is this is the probability of getting a test stat this big or bigger when the null is true, and that's called the p-value. And so this is a z-score. So for z is equal to 1.65 out here, if we went out here, what would be this probability? So we can look at the back of our book here and look at the normal curve, and it gives us probabilities of the middle area. So we said that was about let's say it was 1.65. So we go to 1.65, and that's about 90% of the area is between 1.65 and negative 1.65. All right? So 90% is right here. That's 90%. All right, and you want this area, all that. So if 90% is in the middle, the whole thing's 100%, so that means 10% is in the two tails. But remember, we're doing just one tail, so this would be a p equals 5%, which is sort of the standard cutoff. You'll see that a lot, p equals 5%, a conventional cutoff. All right, so you just happen to land on a conventional cutoff. Now let's look at this one. This looks like what? About, let's say, 2.35. All right, so between 2.35 and negative 2.35, what percent of the curve is there? And what p-value did you guys happen to choose? So let's look that up. 2.35, and it's about 98%. So you said about 98% in the middle. So what if you chose this? We're trying to figure out this area. All right? Well, if 98% is in the middle here, that means 2% extends beyond that. So the p-value for this is just half of that. 2 for both of them, it's symmetrical, so it's 1%. So that would be a p equals 1, which is highly significant. And what about these people here? What did you choose? You wanted even more evidence to reject the null. And this is 2.5, so between 2.5 and negative 2.5, what percent do we have here? Oops. Between 2.5 and negative 2.5. We have 98.76. So let's just round it to 98.8%. So that means outside this region here, we have 1.2% in the two tails together. So our p-value is half of that, or 0.6%, which is very rare. So that only says 6 out of 1,000 times would we see such a big difference if the null was true. And that's like beyond a reasonable doubt. At some point we say, hey, that's so unlikely. We reject that null and conclude that the drug, we have very strong evidence that the drug worked. So that's the idea. All right, so let's just make sure we understand that. So if the p-value is very low, we say the data support rejecting the null hypothesis. We say rejecting the null, this double negative, instead of saying accepting the alternative, because we assumed the null to be true. So we're saying the null is true, and based on the null, this is the probability that we'd see this big a difference when the null is true. That doesn't prove the alternative, and it's certain, right? Okay, so, but we reject the null and basically say there's very strong evidence to support the alternative. Okay. Now, so how low is very low? So as the convention is to reject the null when p is less than 5% and call the result significant. When p is less than 1%, the result is highly significant, but there's no particular justification for these values. They're just very commonly used. Probably just because we have 5 fingers. That's probably why the 5% is such a big deal, the cutoff. If we had 6 fingers, like my son, he was born with 6 fingers on each hand, then probably the typical convention would be 6%, not 5%. We'd be in base 12. So it's just, I want you to know it's arbitrary, and it really depends on the situation, what you care about, which we're going to talk about in a few minutes. All right, so I think you've got that down. And we call, okay, so where we decide to set the cutoff is called the significance level, alpha. And another way to think of it is the probability, the chances of making what's called a type 1 error. The significance level is the probability of mistakenly rejecting the null when the null is true. And it's called a type 1 error. Why? Because when we reject, look, we're assuming the null is true. So this is the probability that we're going to see this kind of data, this kind of result when the null is true. So if we reject the null and say this isn't true, that's the chance of making that mistake. In other words, if this is 5% of the time, we're going to see evidence this extreme, a difference this big, when there's nothing going on. So that means when we say, hey, we set this as the cutoff and we're going to decide for the alternative here, that means 5% of the time we're going to be wrong. We're going to make a type 1 error. All right? So why don't we just set that as low as possible? And why? Because this is when the null is true. Right? But there's another type of error we can make. What if the null isn't true? We're going to have another probability distribution. Let's think about it. There's another type of mistake we can make. Let's say the null is false. Then we'd like our significance test to correctly reject the false null. A type 2 error happens when the null is false, and yet it fails to reject it. Let's think of it this way. All right, so you have these two situations, all right? So let's say when the null is true, you have some way of, some measure, some quantitative measure, a scale of evaluating the evidence for the null. And in the case we've been looking at, it looks like the normal curve. All right, so when the null is true, and let's say it's a smoke alarm, okay? So we have some middle of the distribution, and the smoke alarm goes off. All right? We set it to go off at some, at some point, we're going to reject this, and let's say it goes off here, okay? So now, this right here is the probability of making a type 1 error. So it's like the smoke alarm going off when there's no fire, or the fire alarm going off when there's no fire, okay? It just senses, it's, it senses, it's set to go off here. And so this is the percent of time it's going to make what's called a type 1 error. So you say, well, why don't you set that as low as possible? Because what happens when there's really a fire, right? So let's write that down. So a type 1 error is like a false alarm. A type 1 error, this type 1 error right here is a false alarm. Think of it that way. Okay, nothing's going on, but you're rejecting the null and saying, yes, something's going on, fire. All right, but then there's another probability distribution when there really is a fire, okay? When the alternative is true, when the drug really did work. And the whole point is that we're making this decision under uncertainty. There's some overlap between the two distributions. Otherwise, we wouldn't have to do a significance test. So let's say, and we're doing the same measure here. And of course, there's more smoke, and there's more whatever this is evaluating, the presence of smoke in the air. But also, there's going to be fires that are smoldering and don't give off that much smoke, that are going to have very low evidence. So there'll be some of those. And you might have something that looks like this. On the average, yeah. And let's say that's supposed to be a normal curve too. So when you set your decision maker right here, when the alternative's true and there really is a fire, well, your alarm didn't go off, and that would be a terrible error to make in this case. That's a type 2 error. So let's write that down. So this right here is what's called a type 2 error. It's the probability, this area is the probability of making a type 2 error, and we call that beta, okay? And this right here, alpha, is the type 1 error. That's the probability of making a type 1 error. The probability of making a type 1 error is the area, that area. And we set alpha, and once we set alpha, if these are already, everything else being equal, then beta is going to be determined. Now, look, when we set alpha, we're setting this null cutoff. So you might think, oh, you have to weigh the probabilities, which is a worse error. Well, I think it's worse, even though it's really annoying to have the smoke alarm go off when you're cooking, it's much worse if there was a real fire and it failed to detect it. So you want to set that as low as possible, which then makes your type, this error, you want this to be as low as possible, which then means you're going to have an annoying smoke alarm that goes off all the time. So there's a trade-off between the two errors. The probability of making a type 2 error is called beta. The probability of a type 1 is the power of a test is 1 minus beta. We haven't talked about power, and we will in a minute. We'd like both types of error to be low, but there's a trade-off. Lowering alpha raises beta. We just saw why. So this is beta, and if you call the area under the curve 1, then from here on to the right of this is 1 minus beta, and that's the power of the test to detect a difference that's really there. So this is called the power of the test. This area right here to the left of alpha isn't really called anything. It's just not rejecting the null when the null is true, making that right decision of saying nothing's going on. That's not especially momentous, so people haven't really given it a name. It's like saying, hey, we found out this treatment that we thought of didn't work. That happens all the time. We just don't give that. But this is the power of the test. We want this to be high, the power of the test to determine an effect when it's really there. So that's a basic intuitive idea there. And let's turn the page and get some language down. Now, the language is kind of annoying because there's all these double negatives, so I'm just going to try to help you remember it. So basically, in all these cases, we're making a decision under uncertainty. We never know for certain what the real truth is. Whatever we decide, we'll run the risk of either making a type 1 or a type 2 error. So basically, there's some truth. And either H naught is true, nothing is going on, or something's going on. And then we make a decision. And we either decide to reject H naught or fail to reject it. So let's think about this because it's so many double negatives. So this is H naught is true. Think of naught as nothing. So that is the truth here, is that there is nothing going on, no effect. Let's put a little negative there. No effect. And when there's no effect, there's only one type of error we can make, false alarm. We can say, yes, something is there. We reject the null, and we say there's a fire, false alarm, okay? So we say there's a real effect. That's the only mistake we can make because nothing's going on, all right? So let's call that a real effect, a positive effect. That's the only error we can make. Now, let's think about this. When the null is false, null is the null dull, there is a fire, there is a real effect. The treatment did work. If it was a disease, you would have the disease. If it was a diagnostic test to see whether you had a disease, you'd get a positive. All right? And the only mistake you can make is saying, no, you don't have this disease. That's a false, that would be a type 2 error. So when H naught is false, there's a real effect. And the only mistake we can make is to say nothing's going on, right? So that's a type 2 error. We fail to reject the null when there really is a real effect. Okay, so we say there's nothing going on. Negative. All right, so that's the idea here. And so I just want you to get a picture. We can use this sort of reasoning and how to, like in a randomized clinical trial, the null is that the treatment didn't work. In a jury trial, the null would be that the person's innocent. In a diagnostic test, the null would be that the person is healthy, etc. All right. Why don't we just skip down and look at this situation where, let's say you're being accused, you're innocent, and you're being accused of cheating. Okay, this happens all the time. I mean, at least in my experience teaching these large lectures, during exams, proctors are always saying, oh, this person's cheating. They see their eyes wandering, and a lot of them turn out are innocent. So what happens here? So what is the measuring stick that they're using? Well, it's not really a quantitative, it's more qualitative impressions, but pretend we could translate it into some quantitative axis here, measure of determining whether somebody's cheating or not. So and you could find yourself in this situation. So let's say when you're really innocent, on the things that the proctors actually look at, you might have a score along here. And generally speaking, on the average, people might be in the middle here. Let's think about what I'm talking about. So this is for real, that in every exam, I have a lot of proctors, and they come up to me and they say, I think that person's cheating. Look at that person's, their eyes are wandering, they're looking at somebody else's paper, et cetera, et cetera. And what do? They tell the other proctors, they start looking at the person, they each look at them, they look at whose paper they think they're looking at, they collect the papers, they see how many answers match up. Now, there's a lot of things wrong with that. You could easily be innocent, have your eyes just wandering around. A lot of your answers are going to be the same just because they're right. I mean, or they'll look at the wrong answers, but there's very common mistakes that people make. And if it's multiple choice, how can you really tell you could easily just guess the same thing wrongly as the other person guessed. So, but if there's enough of this evidence at some point, not just on one question, but if you and a bunch of the proctors saw the person cheating and so forth, at some point, they make a decision. Let's say they make it right here. Let's say they actually had a measure and they said, beyond this point, it's beyond a reasonable doubt, and we are going to say the person was cheating. And the consequences of doing that, I mean, these people are innocent, and they've been accused of cheating, and they're likely to get kicked out of the university. The university treats cheating incredibly seriously. And if you get that much evidence against you, it's terrible. And this, let's say it was 5%, we decided to set the market. 5% of the people who are innocent are going to get kicked out of the university and suffer these terrible consequences. So I'm such a softie, and that was keeping me up at night thinking about this, that I might be somebody who would say, I want to reduce, but wait a minute, let's hold on. Okay, well, this is actually what happened. I just couldn't stand doing this. So, I mean, people are always saying they're innocent, and I was tending to believe them or think, oh my goodness, I just can't, what if they, and I just couldn't sleep at night thinking I'd, ruin somebody's life who is really innocent. What if it was my child? So I wanted to reduce that as much as possible. So let's say you reduce it to just a speck there. But then, how about when these students were really guilty, and from survey data I have, 10%, a lot of people have cheated on exams in college. So there's a lot of people who are cheating. So, and they're not getting caught. So these are the ones right here. There are a lot of people, okay, so their distribution on the same measure, yeah, they're more likely to be for the proctors to catch them, but a lot of people are really good cheaters, and they don't have much evidence against them, and these are the people who are cheating who we never catch. And look what happens when I made the evidence so I just moved my deciding line, my null cutoff, so far to avoid hurting the innocent. I'm letting all these guilty people free, and it's ruining the fabric of the class. And that's exactly what happened. The fabric of trust in the class. It was terrible. So what do you do? Well, you're kind of stuck here, right? Unless you think of, and this is what I did because I was so disturbed by this situation, think of a better cheating detection system. So if you think of a better way that separates out these curves so they don't overlap so much. So what I did, those of you who've taken my Stat 100 class know, I give multiple versions of the same exam, that look identical but aren't. And then, and I look just at the questions that aren't multiple choice, and if you copy down the work, the numbers that have no reason, that appear nowhere on your page, and they correspond to the numbers on the other exam, because you're copying down the work, well, then I have very strong evidence, and these curves are very, very far separated. Still, I've never had somebody admit it. They all say, oh, I just guessed those numbers. They all claim to be innocent, and it's possible. They could have guessed those numbers, but it's so unlikely. So at that point, I feel okay about it. So if you're able to separate and find a better detection system, that's great. Another way to do that in another context would be to increase your sample size. When you get a bigger sample size, you have less error. It doesn't apply to that particular example, but certainly to the one that we looked at, to a randomized experiment that we looked at before, those error bars are going to be, the standard errors are going to be much smaller the bigger the sample size you have. Think about it. If you flip a coin 100 times, you're likely to get close to 50%, whereas if you flip it only 10 times, you could have a lot of random variation, a lot of standard error. So that's another way to make your results more precise and separate the two curves. Okay, any questions so far? All right, let's move on then. So what are we doing here? So this is a summary of the reasoning. I think you can read this on your own. Let me just quickly look at it. Let's see, remember the null is the hypothesis of no effect. The null is the null. We assume that to be true. This is important. The only mistake we can make when the null is true is to reject it, right? And that would be a false alarm. The idea is even when the null is true, we're still going to see strong evidence against it just by the luck of the draw some of the time. And the more extreme the evidence against the null is, the smaller the p-value. All right. Why not set that type 1 error as low as possible? We saw just why not. And let's see. So you can read all this on your own. It's just a repetition of what we've discussed. And let's see if you can fill this out on your own, okay? So here we have this situation where this is the truth. Either there is a real effect, in which case the null is false, or nothing's going on, no effect. So let's put no effect, or we'll put a positive for real effect, and then we have our decision. And we're making this decision under uncertainty, so there's always a possibility of an error. So we decide either there's a real effect, or there's not a real effect, right? We'll put positive. I set it up in an easy way here. So we either reject the null and say, claim there's a real effect, or else fail to reject it and say, nothing's going on. All right, so obviously, so what do I want you to fill in here? So when you have a type 1 error, when nothing's going on, and you reject the null and think something's going on, you have a false what? Positive or negative? Like it's a false positive. I mean, this is often, this terminology is often used in diagnostic testing. So the null, let's say you're trying to detect whether cancer is there or not. So the null that you assume is that it's just, an ordinary healthy person, because it's unusual to have a tumor. An ordinary person, just a healthy person, there's nothing there, but this is a false alarm, a false positive. All right, so this would be a false positive, and it would be claiming you have the disease when you don't. So then the other type of mistake is that when you really do have cancer, let's say you really, the effect is real, you really have an effect there, then the other type of mistake you could make is for the test not to pick that up. And that would be a false negative. And that would be, the problem with that is that this cancer would grow and could end up killing you because it was undetected. They made a mistake. So there's a trade-off, and you have to think of the situation to think about how you want to assign what significance, how you want to set this up, which one is a more costly mistake. For example, maybe the treatment for the cancer is really horrible and could kill you, and then the cost of making this mistake and saying that, like, let's say they have to cut off your leg, or, that's pretty horrible, and then they say, oh, sorry, it was just a mistake. You really didn't have cancer. We got your leg here, and it looks good. Well, false positive. That would be that. And for the false negative, it would be, well, sorry, we didn't, you got this, we didn't detect the cancer. If we detected it earlier, like with a melanoma or something, a mole, boy, we could have just done a little, just taken it off, no problem, but sorry, we didn't detect it, and now you're going to be dead in 3 months. So that would be horrible too. So it depends on the disease, you have to weigh these two. So what do I want to say here? So the power of the test is very important to detect an effect that's really there. All right. And just as the convention is to set, for no good reason, but the convention really is they just set it at 5%. You want to have alpha less than 5% for a type 1 error. People like to have power at least 80%, which would mean type 2 error less than 20%. Remember, 80%, if the power of a test is bigger than 80%, that would be this side, the power, then this side, the type 2 error has to be less than 20%. And this usually comes up when you're planning an experiment. Because remember, we said that we can make these curves narrower and adjust this at the start of an experiment if we increase our sample size. Like we plan an experiment, we say, generally speaking, granting agencies won't accept your design of your proposal to do an experiment unless you have at least 80% power. 5%, under 5% type 1 error, and at least 80% power. So why wouldn't they want more power? Why wouldn't they just say have more? If you can just make this as big as you want, why wouldn't you do it? Well, that's just because it's very expensive. It's very expensive, and you might, and you might end up detecting such a small difference that nobody cares about. Because the bigger your power, the bigger the sample size, you can detect these little differences that nobody cares about anyway, and you can spend a whole lot of money doing it. All right, so that's it for now, and next time we're going to do chapter 2. Bye-bye. And we're actually going to look at, in chapter 2, we're going to look at how to calculate these. We're actually going to, chapter 2 is about how to calculate beta for choosing a particular alternative hypothesis. That's what we're going to do. And then we're going, in chapter 3, to look at what I just talked about, how to calculate n for a given alpha and beta when you're designing an experiment. So we're going to go into that next time. See ya. Bye-bye.